So the talk now is Introduction to Relativity Nonsense. There are now many videos on the internet teaching Einstein's relativity. All of them teach various types of nonsense. So I'm going to look at one of these in detail and point out as many of its flaws as possible. The example that I'm taking is nearly a 2-hour lecture, so comment on all that would make this a long video, which we'll have to split up. It's just typical of how relativity is introduced to students, and the video is titled Introduction to Relativity, and hence why I'm calling it Introduction to Relativity Nonsense, and it's by SBCC Physics at that place there, and about SBCC stands for Santa Barbara City College Physics, which is at that place there. So if I go to the video now, it's as you can see here, it's by Dr. Mike Young, introduces special relativity to his students. He's been talking a load of other lectures and so forth about physics, and now he's got on to Einstein's relativity, and so this is an introduction to Einstein's relativity to his students, and I'm guessing that his students might be engineering students by what he's saying. So let me get on to it now.
Last time to get started, so let's get us started and make a quick comment that I think is the obvious. We are now switching gears, going to our last segment, and I think one of the more interesting subjects or topics, although also at the end of our whole book here and at the end of the sequence, this idea of the modern physics is, like I said, is just like all of ours, and I got to keep telling myself, oh, I wish we had more time, but we don't, just like...
So it's a very rushed lecture to the students. He's hoping that he'd wish there'd be more time, and so it's only a brief introduction to the subject. But if you go into the subject even more detail than this brief introduction, then it's just more and more layers of nonsense. So it's pretty much 2 hours of nonsense as the introduction, and then further layers from people like this teaching Einstein's relativity would be more and more nonsense. So let's get on to it.
Didn't have all that much time to do the optics in all its glorious detail, or the thermodynamics in all its glorious detail, or our mechanical ways. But as we get to this last topic of the semester, we'll spend as much time as we possibly could and show you some interesting things, and if nothing else, leave you with hopefully a flavoring, and hopefully even a positive flavoring, of modern physics and modern science.
So he wants to give a positive flavouring, of course. Those of us who get a negative flavouring of it. But anyway, carrying on.
Even though, as you'll see, in terms of engineering, it's kind of, for lack of better words, not mainstream engineering, since one of the first things we'll talk about is only relevant as we get close to the speed of light.
So it's a relevant thing here, hence why I think maybe he's talking to engineering students, because in engineering Einstein's relativity is not usually relevant. You are dealing with speeds which are much less than the speed of light and other things like that. In situations more down to earth where you are not having what are deemed relativistic effects. So the fact that Einstein's relativity is nonsense doesn't really affect too much engineering in most situations. You can be an engineering student without having to worry about Einstein's relativity in your working life in most engineering situations.
And other than a few minor cases, or just a few cases, that's where modern technology is. We don't really go close to the speed of light, or we don't need times accurate to a billionth of a second. But there are some important exceptions to that, and GPS systems are a good example of that. But the science...
So you're saying GPS is a good example of where you need Einstein's relativity, and that's false. If we go on to the relevant bit here, Ron Hatch. Got this person. So Ron Hatch is, if you can read it, perhaps you've already heard that GPS, by the very fact that it works, confirms Einstein's relativity. Also, that black holes must be real, but these are little more than popular fictions, according to the distinguished GPS expert Ron Hatch. So, according to Ron Hatch, no. I'll give a quick look into his talk he's given here. So you get a general idea.
Thank you for inviting me. This is my first Electric Universe one. And however, about 40 years ago, I worked a little bit with Don Patton, and he brought Velikovsky's stuff to my attention at that time. And I helped him a little bit with some orbits way back then. First off, I think I'd better apologize that I'm going to talk more about gravity than electric universe. But I think you can see a few connections as we go along. I didn't know how to organize this. Clearly, I'm going to present it in a way that it wasn't derived. And what I'm trying to do here is simply to show some agreement with facts and ask questions. What's theory say? What does the evidence say? And in what's next, I'm going to talk a little bit about the electric universe.
So according to Ron Hatch, no, you don't have to use Einstein's relativity for GPS. So that's a difference in point of view here. So we've got this person saying Einstein's relativity is used in GPS, and that is false. And that's where we start to get problems with the people who believe in Einstein's relativity. They start making false claims. They start making false claims about experimental results, and they start making false claims about things like GPS. If the claims were true, it would be very impressive. You know, Einstein would probably be right, but their claims, they've got a theory which doesn't really make sense, and they're making false claims about experiment and so forth. So this is the big problem with these people. They're just full of false claims. So he's quickly said about GPS, and it's just a false claim. So we carry on.
Part now really begins to come out as we kind of enter this last phase of the book, and you guys begin to go your own separate ways, both academically and literally as you transfer on to other schools. But the idea is that some of you will go into, well, there's computer science, and some of you will go into mechanical engineering, and some of you will go into science in general. And so some of you will see more of this, others of you won't here. But let's talk about what I would call the pure science now as we start to get into modern physics here. And the author begins here in chapter 39 and calls it relativity, and says, okay, what is...
So he's going by some sort of book which all the other students are going by. I don't think it's quite relevant to have the book. You can look up in most relativity texts similar things to what this person is saying.
relativity. What do we mean by that? In fact, maybe I'll put in parentheses here to emphasize that what we mean here is how somebody might look at the speed of something. That's where we'll get started, relative speeds. And again, this isn't really too new. It's going close to the speed of light that is going to be new. Because if I was driving in my car down the freeway, say 70 miles an hour, and a car goes ripping past me at what you might call 80, that's 10 above me, right? In fact, about an hour ago, that actually did happen. I was going down the road and
And that is Newtonian physics, basically, Newtonian mechanics. So he's starting off talking to them about something they're familiar, Newtonian physics, Newtonian mechanics, and then he's going to go, of course, going to go crazy when we get on to Einstein's relativity. And really, it's sort of, why is there a transition from what is sensible within the context of a Newtonian physics and then go crazy with what Einstein's doing. And one of the justifications they try to give is that there's experimental evidence for Einstein's relativity, and of course that is false. There isn't. When you actually look into it, there isn't, but you've got these people who are saying there is. And I've sort of argued with people like this, and sometimes they admit there's no experimental evidence for Einstein's relativity, and so I then say, why do they falsely say that there is? And they say, well, it then makes teaching Einstein's relativity easier. But of course it is, you're lying to them. A student sitting there is saying, is there experimental evidence for what you're teaching me? And if the person like this says, yes there is, you say, well, I suppose I'll just have to accept the theory then, even though it doesn't make any sense. And so that makes it easy for them to teach it. It's a lie. It's a lie. There's no experimental evidence for Einstein's relativity. And if I go into it, come back to that, I don't know how well I've done with it. Yeah, this is my talk here. On this one, it's called The Lie on Which Einstein's Relativity is Built. And basically it's all a lie. If you actually spend the time looking into all these supposed experiments that confirm Einstein's relativity, you find it's a lie. They don't do what's claimed. So people like this lecturer who's able to get up and lie to the students, telling them there's experimental evidence for relativity, then finds it easier to teach the theory to the students because the students are buying into a lie. It's not until much later do some of them work out that they've been lied to, and that's the problem. Maybe even this person, when he was educated in physics, that he was lied to about relativity having Einstein's relativity having experimental evidence to support it, and he's believed that lie, and now he's teaching that lie to others. So even he might believe the lie. That's how bad it is. It's a lie that's being spread on like Chinese whispers. If I go in, there's Newton, and this is another bit. What is special theory of relativity? I've got another little clips that are interesting. On that one, yeah, later. Hopefully I'll come to, else it's going to have to be in another part of this video. Okay. Yeah, I think I should point out a few other things first. Now I get to. this is a documentary film made by some of us dissidents, particularly David Hillsler, and it points out that most of this talk about experimental evidence for Einstein's relativity is all a lie. When you actually talk to the supposed experts, no, they point out, no, there's no experimental evidence for Einstein's relativity from all these different experiments. So you then sort of wonder, well, what's going on? Why are they lying? And it's really Einstein's relativity is a theory that is led by theory. It is not a theory that is led by experiment. And I've got this one here which I think points it out. This is a little talk here at World Science Festival, and first of all they start with Newton and they go from Newton and they then start talking about Einstein, and I think you've got Professor Brian Greene and other people talking about what's going on. So first of all we've got to listen to about Newton.
He had interesting hair, though.
He lived in England, and he was very interested in the tides, and he thought he had a theory of the tides. He actually did have the right qualitative picture of the tides, but he never...
This is Professor Stephen Weinberg. He's supposed to be respected expert on this sort of thing.
Never bothered to look at the sea in his whole life. In England, he never saw the sea.
Talking about Newton.
But his theory was controversial at the
Newton's
time.
theory.
It was rejected by, on philosophical grounds, by followers of Leibniz and Descartes. It turned out, however, wherever they disagreed, Newton was right. His theory went on from success to success. It had already explained the motion of planets under the influence of just the gravitational field of the sun. And it went on to explain so much else, like the motion of the moon, which is a much more complicated problem, the precession of the equinoxes, all sorts of things, the influence of the planet Saturn on the motion of Halley's Comet, all of that, and it worked so beautifully, and it became, by the end of the 19th century...
So Newton's theory worked, Newton's physics worked also beautifully.
...the paradigm of what a physical theory should be.
Paradigm of what a physical theory should be. Of course Einstein just throws all that into chaos. And we're getting on to Einstein now, I think. This is a Professor Brian Greene who's going to ask a question.
So, just to give a little basic, most people are familiar with this equation over here, which was the law of gravity that Newton wrote down. But what did Newton... How did he view space and time? What was his perspective on that?
Newton was worried about it, and he came to the conclusion, which he stated in the Principia, that there is such a thing as absolute space. He knew that motion at constant speed relative, one observer moving at constant speed relative to another, didn't matter, they were all equivalent. But there was a fundamental frame of reference with respect to which you measure acceleration. And so that there really was a space out there.
Background stage or something?
Yeah, and the time. And it really was not something that was subject to physical intervention. Space was space, and it was there, and it was fixed. And the reason why a dancer's arms go up when she pirouettes, and then when she pulls them down, she goes even faster. That's because she's rotating with respect to absolute space. Newton, in a famous example, the rotating water bucket, yes, described how that is. That was precisely the thing that Einstein tried to get away from.
So what drove people, or Einstein in particular...
So this is Einstein now, really. Why is Einstein going to make the change? We've got Newtonian physics all making sort of sense, and now it's Einstein.
when there's all this observational support behind the predictions of F equals G m1 m2 over r squared.
That's the equations of Newton. All this observational support for Newton.
Come up with a new approach.
Well, it sure wasn't the observations.
Sure wasn't the observations. So suddenly Einstein comes along and we got Newtonian physics all based upon observations. The equations are fitting observations, and this Professor Weinberg is admitting that Einstein didn't go by observations. Pick it up again to emphasise that. It sure wasn't observations.
Famous example, the rotating water bucket, described how
Newton
that
there.
is. That was precisely the thing that Einstein tried to get away from.
Einstein tried to get away from it.
What drove people, or Einstein in particular, when there was all this observational support,
Observational
behind the
support for
predictions
Newton.
of F equals G m1 m2 over r squared, to come up with a new approach?
Well, it sure wasn't the observations. Einstein's general relativity is a wonderful example of a theory-driven revolution, not
A theory-driven revolution. It's not based on observations. And so when you've got other people who support Einstein's relativity and they try to make out it's based on observations, it's false.
observations. Einstein's general relativity is a wonderful example of a theory-driven revolution, not driven by data at all. There were little bits of data that didn't agree with Newton's theory about the motion of Encke's comet and the moon and so on, the precession of Mercury. Most people regarded those as things that would be fixed.
Things that would be fixed. So we've got, before Einstein, people going by Newtonian physics. There was a few things that didn't quite fit in, and they thought, the people going by Newtonian physics thought those things would be fixed. And then at the same time we've got Einstein who's coming along, who's not going by observations, and he's thinking you can just change everything by a theory led by theory, and that is totally false. It's totally ruined physics. Physics has been totally corrupted by this person by doing that, and we've got an omission there of what's going on. There's a lot more there to be said, but things like the bending of light and the periphery of Mercury and all those other things can be explained within the context of Newtonian physics, and there's no real reason for going to Einstein. There's no reason for doing it, and it's just theory being led by theory. And so when people like this are trying to teach students, they don't want to tell students that Einstein is going by theory led by theory. So he's trying to pretend that there are these experiments which support Einstein, and when you actually look into these experiments, they don't prove Einstein's relativity. They can still be dealt with in the context of Newtonian physics. All you get with Einstein is he wants those experiments to be interpreted differently, and if we manage to get to that bit, it's after about an hour, he will, what's his name, Dr. Young, will get into the maths of Einstein's special relativity. And when we get onto that, we'll be saying, why is he putting this interpretation onto that maths, when you could look at that maths which he's going to use, and you could still be treating it the way Newtonian physics wants to treat that maths. So why does he suddenly change it? What Einstein has is just a strange interpretation of how to look at experiments, and that's just nonsense, really. There's no reason for changing from what Newtonian physics is doing to suddenly reinterpreting everything from the way Einstein's dealing with it. And if there's people like this presented that to the students would say, what the F? So you're telling me that this theory is which you're going to teach us now is not led by experiments. And if he was honest, he would have to admit that to the students, that he's teaching them something which is not led by experiments, and the experiments and so forth can still be understood from Newtonian physics. So we carry on now a bit more.
I'll tell you how fast I was going, but it was more than 70. And they still went ripping past me, and I was like, wow. And, you know, I was trying to gauge it from my perspective, and it looked like about 15 over my speed. And I was pushing 80 as it was,
So it's the awful problem on this part. He can talk sensibly and talk in the context of Newtonian physics in the initial bit to the students when he's giving a lecture on Einstein's relativity, and then suddenly he's going to try to switch this around and talk from how Einstein wants to look at things.
Thought, oh my goodness, this person is flying down the road. And so my perspective, I'm thinking, okay, they're going 15 miles an hour. But of course, somebody on the side of the road saying this is close to 95 miles an hour as they're going down the road. And so again, these speeds are relative. Now, that's not even close to the speed of light, but it kind of gets the flavor.
Yep. So with this jargon where he's talking about close to the speed of light, it's supposed to be that when you get close to the speed of light, then suddenly, magically, it's Einstein's relativity. And when we get into the maths further on, which is about an hour on, well, that doesn't make sense. You can still treat it from Newtonian physics, even with speeds near to the speed of light. So it's all completely bogus, this transition from Newtonian physics to Einstein physics at speeds near the speed of light.
That relative speeds is really not so much the issue. It is relative speed and a discussion of faster speeds that we want to get into. And that's where we're going to get started here. We could get into relative positions. For example, you might say something to the effect of, well, how far is it to the door? Your perspective of how far is it to the door is different than my perspective.
But so far in this context, you can still think of those sort of things within the context of Newtonian physics. It's when you get to Einstein, it's going to be all messed up. Issues like that, you're supposed to be then thinking about it from Einstein's way. And as I keep pointing out, there's no reason for changing from how Newton's dealing with it to how Einstein's going to deal with it.
How far it is from the door. And of course that makes sense to you. You go, well, yeah, because you're in a different position. But if I took the position from you to me, and then from you to the door, I would kind of figure out what the distance is from me to the door, right? And so it's relative, positions are relative, but there's a connection between them. All right. We're going to take another look at that. Relative time, I don't know if that's such a big discussion in what I will eventually begin to call here our
and of course, Einstein totally messes up time.
Old physics as we begin to get into some new physics. And so maybe I'll just leave that alone here for a moment and say, let's continue on here. Because one of the first words I want to throw out here is to say, for the last either 2 or 3 semesters, or 3 or 4 if we count Physics 102 in there. But for the last 2 or 3 semesters, and maybe I'll just call it 3 since this is the end of the book, although I know some of you haven't done the Physics 122, and half of you, maybe even more than half of you, next fall we will. But this at the end of the book is really what we would call classical physics. It's the physics that kind of began with Galileo and Newton and mechanical laws, and from then we did our other ones like thermodynamics and electricity and magnetism if you did Physics 102. But all of this really fits into a category of what we call Newtonian physics or classical physics. And
Yeah, and of course the transition from all that to Einstein is just nonsense. So that's what he's building up to. Just trying to make a big bluff and transition on to Einstein when there's no experimental evidence for Einstein. All Einstein has is a weird reinterpretation of experiments and observations, when you really could just carry on with Newtonian physics.
when we looked at it, we did things like this. I mean, one of the things that we did back here in classical physics is we said the kinetic energy is 1/2 mv squared. I mean, that obviously...
And of course, Einstein messes up things like that as well. So you've got Newtonian physics with that, and Einstein wants to mess that up. Einstein just messes up everything.
He takes us back to Physics 121. We did that in Chapter 7. Oh, we also got that, if you recall, by saying this is the integral of the work. And the force, at least net force, was mass times acceleration. I mean, clearly Newton there. This is Newton's second law. And so this all is referred to then as classical physics or Newtonian physics. And that's what this last unit is about, kind of introducing you to something beyond Newton. And
so what he's saying is this talk he's got here, introduction to relativity, i.e. introduction to Einstein's relativity, is supposed to be going on beyond Newtonian physics. And of course I'm saying that's all nonsense. You've got Newtonian physics is quite sensible, and then he wants to add this talk on top of it, and you're just piling on loads of nonsense. So carry on.
Really showing where Newton's laws are incomplete. They were not perfect.
Saying Newton is incomplete. I think you might say that again in a minute as I pick it up.
Probably a terrible thing to say after 3 semesters of some really hard work, but we did it all wrong. Well, that's a little strong. We didn't do it wrong. We did it approximately right.
So he's saying now that up to this lecture they were dealing with Newtonian physics, and that Newtonian physics was approximately right, and he's wanting to add this Einstein's relativity on top of it, and I say that's wrong. This is what he's adding on to Newtonian physics in this sort of lecture is just nonsense. So I know a bit more about Newtonian physics than this person. He doesn't. So what happened was you had lots of people working on Newtonian physics after Newton wrote his books, Principia on mathematics and the optics and so forth. So you had what were called sometimes called Newtonians. So in the 18th century I found out there was this person called Roger Boscovich, and I'm calling him the founder of modern science, and I've translated this book from Dr. Dragoslav Stogovich, and I'm saying Boscovich provided the foundations of modern science, and Boscovich's theory is a unified field theory, and Boscovich is 18th century. So what you had from Newtonian physics is a unified field theory of Newtonian physics, and that happened in the 18th century. And so go back to so when you've got people like this, they've suddenly missed that. He's missed that out. They taught the students Newtonian physics, and he never gets to what is the unified theory of Newtonian physics, which was Boscovich's theory. He never gets to that. He never gets to teach them that. he presents to them Newtonian physics, and Newtonian physics in an incomplete form. It's not in the completed form of Boscowicz's theory. So that's all he's teaching. He's teaching an incomplete Newtonian physics. He's not teaching the unified theory of Newtonian physics. And then he just jumps onto talking about what Einstein's dealing with, and Einstein is just introducing a load of nonsense into physics. So that is one of the big messes they're making. They are missing out a great deal of Newtonian physics when they jump on to Einstein. Carry on.
There's more to it. And that's what this next section is. This next section is saying, let's look at some new extensions of Newtonian physics. Probably the best experiment, it starts with an early example. And so let me go back in history. I think kind of to make this make sense, you have to realize what was happening at the end of the 1800s and the experiments that were being done. One of the common one was to take a little electron and a metal plate, charge it positive, and let this positive charge pull the electron, put a little hole in it, and look at the kinetic energy, or to look at the speed of that electron. How fast is it going? Now, for some of you, this is kind of an unfair discussion because you haven't done electricity and magnetism. Others of you have. So I won't dwell too much on it, but I will remind you of this idea back in Physics 121, that if we do work on an object, whether it be a big object like a car or a little one like an electron, its kinetic energy should be equal to 1/2 mv squared. And that's what this little electric field would do, whether or not you've had time or had the class yet to talk about electric fields. So one of the early experiments would charge this plate up to 200,000 volts. And so you can kind of see in history that we needed to really understand electricity first, and then from there, little electrons, before we can get things going really, really fast. And so let's say we charge it up, and maybe I should spell it out for some of you who haven't gone through there, but we've got this at 200,000 volts. The work done on it is the charge of the electron times the voltage. Now, again, for some of you, you don't know that, so I'm just going to say that. And again, it's not the electricity part I'm really interested in. It is the moving electron that I'm interested in. Because if I put the charge of the electron, and then I put in my 200,000 volts, and I set that equal to 1/2 times the mass of the electron times speed squared, what do I get? And so, again, into the late 1800s, these experiments were performed. And they get a speed that comes out to be about 88% the speed of light. Now, let me pause right.
So what's he going to do? He's going to do a calculation with a higher voltage, and he's going to say that that doesn't come out in agreement with Newtonian physics. And unfortunately, what he's doing is he is not presenting to the students the unified theory of Newtonian physics. As I pointed out, the unified theory is from Boscovich, 18th century. So he's just suddenly jumping from Newtonian physics when it was in its incomplete form, doing a calculation, and he's jumping from that and he's jumping to special relativity, and he's missed out a great deal in the historical development of that. So he's basically talking nonsense. He's just censored a great deal of the history of physics in his explanation, and he's also so there's no, as I've always pointed out, there's no experimental evidence for Einstein. All you've got is Einstein's theory being used to reinterpret the experiment. So this is not support for Einstein either.
Right there, because this is probably worth mentioning. What is the speed of light? All right, we just got done with our optics, obviously, so it's 3 times 10 to the 8th meters per second. And of course, we could actually mathematically multiply this out, but we usually don't. We usually start to write things as a percentage of the speed of light. So instead of me just putting a big number over here, let me just say, this is a fast speed. This is 88% of the speed of light. And when they first did this experiment, they kind of hooked it up, they measured the speed. They noticed the speed wasn't quite 88% of the speed of light, but you know, they probably blamed it on their partner and said, well, within reason, we got that. But here's the most interesting part of this, is then they said, well, as our technology develops, maybe we should charge up the plate even more. How about 400,000 volts? And so whatever it took to eventually get to 400,000 volts, we can then run the experiment. Now the reason that's a nice number is because isn't that twice as much work here? And so we would have a different number here. We would have still the charge, 1.602 times 10 to the minus 19. We would also have then this 400,000 volts. We would set it equal to 1/2. We would set it up to be 9.11 times 10 to the minus 31. We'd get V squared. And if you actually get your calculator out and do this one, you come up with about 125% the speed of light. So the idea is, okay.
So he's going to say that's not what they got when they actually did the experiment. And what he's missing out is, as I pointed out, that there's far more to Newtonian physics than this. So he's presenting a incomplete picture of Newtonian physics. He's not dealing with how the Newtonian people were trying to deal with this experiment within their context. And so he's saying, and he's making these false claims. So he's got this false claim that it then requires Einstein's relativity. If I can pick up a bit more on that, get on to 30.
Should and have the potential to go faster than the speed of light, and yet they don't.
They don't.
And no matter what they've done, and they did a bunch of other experiments too.
Yeah.
Everything we've been talking about
So
up to
what he's, if I jump to this bit, I can explain it rather than him have to waffle on about it. What you've got is this axis is size, and this batch is speed, and what he's going to say that when you get down to a very small size of 10 to minus 10 meters, which is a subatomic size, below that area, Newtonian physics breaks down, and it's quantum physics, and above it, it's Newtonian physics. And then he's going on to the speed bit. When you've got to put down a speed of light there along that axis, and the nearer you get to that speed, the less Newtonian physics works, and then you go on to Einstein's relativity. So that's the picture he's going to draw. If we can jump onto it, 15. Okay. Jump too far.
but it is really slow compared to the speed of light. And so when I say slow, I mean slow compared to the speed of light. And so this little area, this box...
Yeah, so in that little box, that's supposed to be Newtonian mechanics, and outside that box you're supposed to have Einstein's relativity up there, and then it's quantum mechanics down there. And that's all, of course, based upon him not dealing with the unified theory of Newtonian physics, which is this person again. So it's a sudden jump from an incomplete Newtonian physics to Einstein's relativity. and so forth. He's not presented it properly. It's a cut short history of physics, basically. There's more to physics history than that. And when we go on to, if we go to 2010, I'll just pick it at 2010.
Are learning lessons that goes on here, and we will discover here that, hey, there is more stuff going on. Those of you who had me for 122, you saw this on the last lecture. Left you with maybe a weird taste in your mouth, because we spent the whole semester talking about magnetic fields, only at the very end to say what? Magnetic fields don't really exist. They were a human perspective of a misunderstanding of what really goes on at close to the speed of light. And so we have to kind of modify our thoughts. Now, don't get me wrong. That doesn't mean any of the stuff that we did in Physics 122 is useless by any means. What it means is we can still do and think about magnetic fields. They work great in terms...
Anyway, this is back to the box. That area there, it's supposed to, well, that region there, that is supposed to be Newtonian mechanics. That one there is quantum mechanics. That one there is Einstein's mechanics, and that area there, they don't really combine those two things. And so that's false, basically. From the unified theory of Newtonian physics, it deals with all of it, and it's that person again. Where's he gone? Where's he gone? Where's he gone? Boskowitz there. Boskowitz theory dealt with all of it. Dealt with the subatomic realm and dealt with the relativity issues. And Einstein's just messed up relativity, basically. Because if you look at the history of relativity, it goes back to at least Galileo. Galileo was doing relativity, and people like Boskowitz was doing relativity. So when you get on to Einstein, he messes it up, and it becomes part of the education system to teach a load of nonsense. Next, you're going to get on to the Michelson-Morley experiment. He's going to make false claims about that again, because he's thinking in terms that Michelson-Morley experiment supports Einstein's relativity. And if we go on to that one, this article by John D. Norton, called Einstein's Special Theory of Relativity and the Problems in Electrodynamics of Moving Bodies that led him to it. If we go to the relevant part, so this is what Norton is saying. Many have tried to emulate Einstein and do in their fields of science just what Einstein did for simultaneity, space and time, when Einstein changed all those things. For these reasons, many have sought to understand how Einstein worked his magic and came to special relativity. So basically it's magic what Einstein did. We've suddenly got Newtonian physics, and suddenly Einstein does a load of magic, and suddenly it's on to Einstein's relativity, and it doesn't make any sense as to why all the changes Einstein's doing. And as I pointed out, the people who support Einstein's relativity then start making false claims about there's experimental evidence for Einstein's relativity, when really it's just a reinterpretation of experiments. Carrying on what Norton says, these efforts were long misled by an exaggeration of the importance of one experiment, the Michelson-Morley experiment, even though Einstein later had trouble recalling if he'd even knew of the experiment prior to his 1905 paper. That's his famous paper on Einstein's relativity, special relativity, and as I pointed out in one of these talks here, it's Weinberg, is that the right one? It's this one here, relativity since Einstein. Weinberg was pointing out that Einstein had his theory led by theory. It wasn't led by experiment. It wasn't led by observation. So Michelson-Morley experiment wasn't supporting Einstein's relativity. Einstein's relativity is just a reinterpretation of that experiment. Right, and so this is what Norton's pointing out, that fact. This one experiment, that's the Michelson-Morley experiment, in isolation has little force. Its null result happened to be fully compatible with Newton's own emission theory of light. So what he's saying is Michelson-Morley experiment is compatible with Newton's theory, Newton's physics. You don't have to make a transition from Newtonian physics to Einstein by the Michelson-Morley experiment. That can be carried on just by Newtonian physics. And the thing to dispute is that there's a null result. People have, that's one of the things that there's a lot of argument over. Was it a null result? It wasn't quite null. It was a non-null result, and it's approximately null. So we carry on. Located in the context of late 19th century electrodynamics, when ether-based wave theories of light predominated, however, it presented a serious problem that exercised the greatest theoretician of the day, and presumably he means Einstein by that. So basically what he's saying, this is going back here, go back to top. Norton is admitting that Michelson-Morley experiment is not proof of Einstein's relativity, and it can still be dealt with in the context of Newtonian physics. What I think he believes, though, is that other experiments are the ones that support Einstein's relativity, and of course he's false on that. So this is what you get with people who like to believe in Einstein's relativity. Sometimes they will say something that's correct, and then they mix it in with something that is wrong. So despite his admission there that the Michelson-Morley experiment doesn't support Einstein's relativity, this Professor Norton wants to believe that other things do support Einstein's relativity. So he gets some things wrong and some things right. And if we go back to this one, I think this person is going to get it wrong on the Michelson-Morley experiment. If we get on to that.
Of building a magnet and putting it on the wall, and building a magnet and making a motor, and building a magnet and making the locks on my car go up and down. But they really aren't the science of what's going on, and that's this whole idea. And so there becomes a kind of a divide now between the science, perhaps, and the application of the science, and how do we want to apply it. So I'll say the same thing here. Although we're going to go into here, don't forget F equals ma. Don't forget the kinetic energy is 1/2 mv squared. If you find yourself in a career where you're building a car, go ahead and use F equals ma. Unless this car is going 90% the speed of light or something. It's fine. Continue on with the same process. That's not really the point of this introduction. The point of this introduction is to say there is more going on, and we don't have to consider the more going on unless we are getting close to the speed of light. And
that's when they mess up, when they get close to the speed of light, when they think they've got to use Einstein, they start messing up.
Like I said, that's our first step. So that's the introduction to the introduction of modern physics, is to say that there is quite a bit more going on, and I think that picture shows it really well. All right, here's another good experiment that shows it really well. It comes right out of our optics and our interferometer. And so the lab we did this week, or for some of you will do today, is to kind of take a look at the interferometer again.
Yeah, this is the Michelson-Morley experiment.
And it was Michelson.
Michelson.
Yeah, and I guess his buddy Moray.
Moray.
And so the Michelson-Morey experiment, who said, let's try this. The Michelson interferometer, if you recall here, was taking some light. In the lab, I'll call it laser light. They didn't have laser light at that.
And I'm pointing out to you, as the article article dealt with, points out that this experiment can still be dealt with in the context of Newtonian physics.
Time, so we'll call it sunlight or something, but some light. And if you remember, it hits that little splitting mirror, bounces off, and comes over here and hits one mirror, and hits over here another mirror, bounces off, comes here, bounces off, comes back, and we look up here on a screen and ask ourselves, well, what are we going to see? And maybe for completeness, I'll point out that some light goes over there. And so the 3/4 of you that have already done this lab, you noticed that what we had in the center was a dark fringe or a bright fringe or maybe even something in between. It all depends upon the spacing between these two mirrors, the relative spacing. And in the lab we moved the mirror a distance d. Well, it was Morey who came to Michelson and said, hey, let's use your interferometer because I've got an idea here. I've got an idea to kind of figure out how fast is the Earth moving through the universe. And his idea makes sense, at least for the science known at the time, and the science you have been taught so far. He said, look, here's, say, the Earth, and the Earth is moving around the sun. We know that much. What we're not sure about, though, is how much is the solar system moving around the Milky Way. And I'm not even sure if they knew that much. But even then, how much then is the Milky Way expanding out? And I'm sure they didn't know the Big Bang in that point. And so that was just the question. What is the overall speed? And here's their logic. Their logic is, if I were to perform this experiment with this interferometer on a moving object, how would I analyze it? How would it be different than if it was on a stationary object? You see, what we talked about in our optics is as if the Earth was stationary, as if the Earth wasn't moving. And if the Earth isn't moving, what would happen is it would go down and back, it would go down and back. Let's just say that those paths differ by some number such that you get a dark spot right there. Okay. We know then, if you move the mirror, it changes from a dark to a bright. But what if it was moving? How would this little discussion, how would this interferometer be discussed and analyzed if it was moving? And let's just say it was moving in that direction. And so this is why, as I said, Morey came to Michelson and said, you know what, let's re-look at your interferometer, but let's do it from a viewpoint that the Earth is moving for a second. Because if you do that, what happens is it would look as if this mirror was moving along. And so the laser beam would come in, and let's say, here's the light as it leaves. Now, at that point, here's the mirror. I'll call that T naught. But as time goes on, the mirror's going to be moving back. Now, how far it moves back really kind of depends on how fast the Earth is moving, or wherever this object is that is doing it. So it's moving back a little bit, and then of course the laser light is going at the speed of light, so it's going to catch it, right? And so maybe that beam hits right here. I'll call this T1.
I don't think it's very tidy, but basically what you're dealing with here is maths, which is normal Newtonian physics maths, really.
Then the light reflects back, and this mirror may be back here to T2 by the time the light comes together and hits this splitting mirror. because the splitting mirror is kind of doing the same thing. T naught, T1, T, actually maybe I should call T naught when it actually hits the splitting mirror, T2. So by the time it gets back, it actually hits the mirror right there, fair enough? And then that's what goes off to the screen. And then I think you'll see that the distance that this beam traveled is not simply that doubled. The distance the light traveled would be a bit more complicated. Now, let's not go through a complete analogy how to discuss this, but I think you can see that I would have to take the time it would take to go from here to here to hit the mirror, then from here to here to get back to there. Fair enough? And I would call that the distance of that light path. And then let's look at this one. How about this guy down here? Well, again, when the light beam hit the splitting mirror, this lower mirror could be thought of as being in this position. There's T naught. But as it comes down, it actually is going to hit right here. Let me call it T1 prime, only to say this is the time when it hits this mirror. But it's probably different than this one, because this one's coming down at an angle, and this one's going straight back. And so however much time it takes to go from here to here probably isn't the same as it takes to go there to there. And then likewise, here will be T2 prime, where it comes back and meets up with right there. And that's a little big picture. Maybe I should have just, I went past my mirror. But it would be 1, 2, 3, or something like that. And as I said, this would be a fun derivation into analyzing it. You actually did this. Do you guys remember the swimmer problem at the beginning of the semester? No? You had a swimmer on a river. You had two swimmers. One went across the river and back.
And it's a fairly well-known example of the swimmer problem, dealing with speeds or with velocities of a swimmer in a river, and it's dealt with in the context of Newtonian physics. And so same thing with the Michelson-Morley experiment. It's still being dealt with in the context of Newtonian physics, the maths of Newtonian physics. Same with the swimmer. It's dealt with in the Newtonian physics context of maths. And he's saying that that swimmer problem was introduced to these students earlier when all they knew was Newtonian physics, and so that was the maths they were then using for it. Carry on.
Another one with the river and back?
Newtonian physics, maths.
And the reason I picked that one, even though it was way early in the semester and very few seem to remember by the time we get here, but by the time you go through all that derivation, you were supposed to come up with that these times weren't equal. And so the effect you see on the screen is different than what you would have seen here. And really that's all we need for today's discussion, is to convince you that it will be different. Oh, did I see a question?
Oh, is the laser standing still, or is it?
Well, then the laser would be moving too, so the laser and the table and the classroom, they're all moving along on the earth. So, all right. But here was then the Michelson-Morley experiment. They said, we got this. Since this pattern would be different this way and this.
I think he's not really dealt with that very well, because the swimmer things I've looked at, they talk about the speed which the swimmer recognises for himself, the speed which a person on a boat would recognise as the speed of the swimmer and everything else, and the speed as recognised as a person on the riverbank looking at them. And as far as the context of Newtonian physics, if you weren't getting a motion effect within the Michelson-Morley experiment, then that means you are moving with the ether. And it's like the swimmer who's moving with the river flow. So either you're outside of the river flow on the river bank watching the river flow, which is equivalent to watching the ether flow, or you are in the river moving with the ether, moving with the river, and that's equivalent to being in the ether and moving with the ether. And that's what the Michelson-Morley experiment shows. You are like the first swimmer in the river, moving with the river, equivalent to moving with the ether.
Way. There should be an interference
Still all
pattern
Newtonian
on
physics
here
maths.
because of the different effects with the motion and perpendicular to the motion. That's what I want to emphasize. Because although when you get a pattern on the...
So he wants to emphasise that, and I think he's missing the point entirely. It's about being in the ether, moving with the ether, as opposed to being outside the ether, not moving with the ether.
Green, and you get bright, dark, that by itself doesn't tell you anything, but here was their genius. Let's do this. Let's look at the pattern on the screen while we rotate it. And so you mount this whole interferometer, and I think theirs was like 20 feet, 26 feet long or some large amount. And they look at that pattern and they realize if you rotate this, one arm, which was going with the motion, is now going to be perpendicular to the motion. The other arm, which was perpendicular, is now with the motion. And there will be a difference between those two, and the change will be shown up on the screen. And the fringe pattern, they could count. Bright, dark, just like you guys did in lab. And from that information, we should be able to figure out how far the mirror moved, which is really telling us how fast the Earth is moving. Ah, brilliant, right? So only give it a try. Guess what they find? Nothing. Absolutely nothing. Frustrated by it all is why they kept building.
That's where he's false. He's saying it's absolutely nothing. He's claiming a null result, and when you look into it, it wasn't completely null. It is a non-null result actually, and they're only treating it as null as an approximation.
Bigger and better interferometers going, there's got to be an interference pattern. Now I suppose you may argue, well, the Earth's not moving then. Well, they decided to wait a half a year because perhaps...
The Earth isn't moving if you treat it as an inertial frame. You have to treat it approximately as an inertial frame. In actual fact, it's a non-inertial frame. It is accelerating, but treating it as approximately as an inertial frame, and then from that frame there is no motion. You can't tell by the relativity principle who is moving for inertial frames, and the relativity principle is part of Newtonian physics. It's the extra bit that Einstein wants to add about the constancy of the speed of light in vacuum, which is going to mess it all up. But straight away from Newtonian physics you do have the relativity principle. So in an approximation, the Earth as an inertial frame, you're making measurements from that inertial frame, and you're not going to get any motion, detect any motion of that frame. So it's still consistent with Newtonian physics. I try to emphasise it's only approximately inertial frame.
They just were at the right spot when they did the experiment, and the Earth wasn't moving. But they know 6 months later they're going to be moving the other direction. So they try it again 6 months later. Guess what they get again? Nothing. Right. So,
and the Earth has approximately an inertial frame, stays approximately inertial frame.
this is often referred to as the most famous null result. Because it looks like something is not going as planned. But what they indirectly discovered is the same thing on that first experiment. What I was trying to show is there's something about the speed of light. Something that is more than just...
And that's where they go wrong. Something about the speed of light. No, as pointed out by Norton, there isn't anything of that from the Michelson-Morley experiment. There's nothing from there, from this paper here. As pointed out, that experiment need not be interpreted by special relativity, where special relativity has all this about constancy of the speed of light in the vacuum. Where is the other one? The light, and this one. That's my little talk here on the lie upon which Einstein's relativity is built. So when they start making these claims about the constancy of light of speed, then they are really just lying about these experiments. Then there is an omission in what was a banned lecture by Rupert Sheldrake, where he talked to somebody expert on this, and they never really measured the speed of light to be constant in the vacuum. Speed of light in the vacuum, free of fields such as gravity, they never actually managed to get it as constant. And so what they do is they just want to define it as constant, and that is where they start to mess it up. They're not getting it from experiment. Instead, they are imposing on experiment this condition of light speed constancy, which means a reinterpretation of these experiments from the way that Newtonian physics would deal with them. And development maths is going to come up in about another 10 minutes or so. He's going to start working at the maths for it, which is really just Newtonian physics maths, and then he's just going to make a little mess with it, and he's going to do it the way that Einstein wants to interpret that maths. So it's just messing up the maths, and wanting to interpret it from Einstein's strange way of doing it.
the speed of light. In fact, I wish we would change the name speed of light to universal speed or speed of the universe.
And that's messing up even more. So people have all these sort of like beliefs about the speed of light in vacuum, free of fields of gravity and other fields, and they think it's something like a universal speed or a limiting speed and all these other weird things, and it's all based upon messing up the maths a bit on that direction.
Yeah, because speed of light does not give the true justice behind the physics of this number.
No.
There is an
You just messed it up with that number, really.
important idea behind this. There is something about built into the universe about that speed. And we as humans discovered light going at that speed for the first time. But that's long before we discovered the speed, say, which gravity goes. Because it too goes the speed of light.
So really he's making an assumption that gravity goes at that speed. Really, that is still an open question. I don't think even I don't think that the majority would agree to that sort of claim. Even the people who believe in Einstein's relativity would agree to that claim as being so far confirmed by experiment. So he's imposing upon his own opinion upon that issue, and it's going against what they're doing. Yes, at the moment they're doing things like gravity wave detection, where they trying to do experiments to detect gravity waves, and they haven't so far detected them. And if you were detecting them, you would be working out what the speed those sort of like gravity waves would be going at. So him saying that gravity goes at the speed of light, well, now he's just going against what the majority of people who even believe in Einstein's relativity would be thinking. He's just getting that totally wrong.
And everything we discover goes either less than the speed of light or at the speed of light.
So he's imposing all that sort of like belief onto it now.
And so this speed of light is, as I said, far more important.
It's sort of like becoming some way of imposing a load of nonsense onto physics.
And so this null result actually opened the door to Einstein here. Although I guess there's some historical debate whether Einstein even knew about this experiment or not. But let me go with it. He certainly knew other things about it. But one thing that didn't seem to make a whole lot of sense, yet seemed to be true from the experiments, is that all observers seem to show that the speed of light is 3 times 10 to the 8th meters per second.
Which is false. As I've dealt with in my the lie upon which Einstein's relativity built. That is the lie. It's just an outright lie. He's trying to make out that there's experimental evidence which Einstein's relativity comes from, and as pointed out by this other one from this little talk, reality since Einstein. Einstein is not going by experiment, he's going by theory led by theory. So pretending that there is an experiment or experiments which Einstein's going by is a total corruption.
It didn't matter how fast you are moving. You see, here was the argument. The argument was, very simply, that the reason you plan to get a different pattern on here is because when you go to analyze this, like you guys did for the swimmer in the river, is you analyze it by saying, if the mirror is moving backwards, say here at half the speed of light, and then the light is traveling towards it at the speed of light, you say it is then approaching, if you were on the mirror, let's say, looking at the light, and you're saying, okay, come here, light, bounce off the mirror. You're looking at that light, and you're saying, well, it's traveling half the speed of light. Well, if the light was still coming at the speed of light, even though I'm moving at
You're just totally messing it up,
light,
Newtonian physics maths being used on both from Wall experiment
it wouldn't matter
and
how
the
much the
swimmer.
Earth was moving. It could be moving a little, it could be moving a lot. It was all irrelevant. Everybody would see the speed of light the same. And so this kind of brings up that question. Is it possible that the speed of light looks the same regardless of how I'm moving? So if I'm on this mirror moving backwards, I see the light still coming to me at the speed of light? Is it possible then?
It's not possible, and there was no evidence for it. But he's carrying on falsely claiming there is evidence.
That if I'm on the mirror sideways and the light's coming down at an angle, is it moving the speed of light? Could it be possible that if I'm in a spaceship going this way and I turn on my flashlight and the light goes out and my spaceship is going half the speed of light, the light leaves at what speed? The speed of light? Or does it leave at half the speed of light? And if it leaves me at half the speed of light, what does it look like to you? And so the whole point of this beginning part is that...
And all that doesn't really make sense too much until you get to the maths, which is coming up in about 10 minutes. And you're going to mess up what is basically Newtonian physics maths. So we're getting to that. Goodness more. Right, there
Our experiments begin to show something interesting about the speed. It wasn't just the speed of light. There's something more here in the fundamental nature of the universe. And as bizarre as it may seem, here is kind of Einstein's approach. He says, look, let's just take this as a given. We call this the first postulate, then, of special relativity. And
so he's getting that wrong. Most books seem to say it's the second postulate about the speed of light being constant in vacuum fields, the effect on it. So he's getting that wrong. Well, going contrary to what most relativity people say.
Look, without explanation, that's why it's a postulate. Let's start here. Let's start with this idea, because that's what the experiments seem to say. I don't really understand why. I'm not even going to try to understand quite yet. But I'm just going to start by saying, if I'm in my spaceship and I go along and I shine it, how fast does the light go away from me? Well, since it's light, it goes the speed of light. And so the fact that I am going half the speed of light and I shine it, it still goes half the speed of light. And if you, sitting on the side, watch the light go away from my spaceship, how fast does it go? The speed of light. And so that's where we want to start. We want to start, is that even possible?
No, it's not possible.
It doesn't seem like it, does it?
It's not really possible unless you're going to start messing up things like time and distance. And when you start doing that, you're going to mess up other things like kinetic energy and momentum and mass. It's just a continuation of effect. You decide to mess up on the bit about the speed of light, and then you're just going to carry on and mess up everything else. So sensibly, it's not possible. But unfortunately, the people who believed in Einstein's relativity have not been sensible, and they just continue the process of messing up.
But here's where the brilliance of Einstein comes in. And I should probably even say the boldness of Einstein comes in. Because keeping in mind these experiments...
And the people who are opposed to this think it's nonsense, who think it's more like the stupidity of Einstein. So what he's thinking is a genius thing. We would look at as stupidity.
Keeping in mind that there seems to be something universal here, something about the speed of light. Let's do this. Let's kind of run a simple experiment here. Let's do this. You'll notice that a lot of these discussions involve trains, because that's how Einstein explained it all, which I think in our time and age, or maybe not our time and age, but at least our location in the world here, trains aren't that very common to us. We should change it to a car, I think, or something. But nonetheless, the Einstein had his apartment.
So we're getting on to the maths now, and I will have to pick this up in the next video clip. So that's it for the moment. I've pointed out all the problems now. He's got up to 39 minutes 13 seconds, and he's got more than an hour to go, and now he's going to get on to the maths. That's the central bit, and he's going to mess up that maths, and then he's just going to carry on and on and on. It's just an awful process of keep making a mess. It's sort of like Einstein seems to be. He's probably one of these people you think is a bit autistic, who makes a mistake, and rather than correct the mistake, just adds more mistakes to it, and so it's a mounting of mistakes, and it is then intimidating, because there's so much of it. It's piles and piles of papers of this nonsense, and it's all building on top of each other. It's just a mounting of it. It's intimidating. You sort of like say, well, it's nonsense to say the speed of light is constant, but then they say, oh yeah, that's okay because time changes. What? Relative time is not absolute anymore. I said, well, that's nonsense. It mess up length. And then they say, well, that's all right because length is contracted, length changes. So you messed up time, you messed up length, and then what are you going to do? They're going to mess up energy as well. They're just going to carry on. It's just building upon it, just building upon this mess, and it becomes more and more and more. Rather than correct the mistakes, it's just build another mistake on top of it, and more and more until you've got a ginormous mountain of it. It's the same sort of thing when the science people believed in the Earth-centered theory, when they went by Ptolemy and Aristotle. They just built a mountain of mistakes on top of that, and they've sort of now decided to do exactly the same thing from Einstein. Einstein makes a mistake, refuses to correct it, and keeps adding more and more mistakes on top of it, and people like this have picked up on it, and they've added more of their mistakes on top of it as well. So that they start making false claims about experiment and everything else. So we'll pick up the maths next time when he decides to mess up the maths. And when you see that he's messed up the maths, you see what they've done is then imposed that messed up maths onto experiments. Mess up the maths and then mess up the experiments to conform to that messed up maths. It's just a continuation process. They won't stop making their mess. So we'll pick it up next time. Thank you.
Or is